Welcome to qnawire.
For this problem, we will let point C be the intersection of axle C and rod DE, and point G is the mass center of tube AB. So the masses and the moments of inertia about vertical axes can be written as follows. So we know the mass of tube AB is given as 1.6 kg. The moment of inertia of AB is 0.0025 kg meter squared. And the moment of inertia of DCE, which is the rod tube together, is 0.3 kg meter squared. Now, initially, we have state 1, in which the tube is fixed with a cord. So our values for state 1 are the position of the mass center relative to point A in state 1 is equal to a half times 125. So it's the center point of the tube AB, and this is 62.5 millimeters. And the system is rotating with angular speed omega 1. Omega 1 is equal to 5 radians per second. Then in state 2, when the cord breaks, the tube is free to move. And the position of the mass center G relative to end of the tube A in this state is equal to 500 minus 62.5, which is 437.5 millimeters. And we'll let the angular frequency at this point, omega 2, be equal to simply omega for simplicity. And finally, we have that V bar, which is the speed of the mass center of the tube, is equal to R of G relative to C times the angular frequency at which the assembly is rotating, omega. So using the principles of conservation of momentum and impulse, we can see that in the initial state, when tube AB is stationary, the center of mass, point G for the tube, moves with linear momentum MAB V bar 1. The tube rotates with angular momentum I bar AB omega 1, and the rod rotates with angular momentum I DCE omega 2. Points A and C coincide. Then we have an impulse, which has an X and Y component when the cord breaks. And the final state is when the tube hits end B of the rod, and now the linear momentum of point G is MAB V bar 2. The angular momentum of the tube is IAB omega, and the angular momentum of the rod is IDCE times omega. So we will use this information and we will find moments about point C. So if we take moments about point C, we get that I bar AB times omega 1, which is the moment of the mass center of the tube, plus I bar DCE omega 1. So these are the moments for the initial position when the cord is still intact, plus MAB V bar 1 times R of G relative to C in the first position. And since AB is not free to move, that moment is 0. And this is equal to I bar AB, and now we're looking at the second position, omega 2 plus I of the entire rod and tube system, I DCE times omega 2 plus M AB, the mass of the tube, times V bar 2 times R of the mass center relative to point C for position 2 of the system, RGC2. So we can write this by pulling out the omegas as common factors. So we can write this as I AB bar plus I bar DCE plus MAB RG relative to C for position 1 times omega 1. Well, this is RGC now becomes squared since we replaced the V1, the V bar 1 with omega 1 RGC. And this is equal to, we'll do the same on the right hand side, I bar AB, the mass moment of inertia of the tube, plus the moment of inertia of the system, I bar DCE, plus the mass of the tube, MAB, multiplied by RG relative to C for position 2, and that's squared. And again, that's multiplied by omega 2. So essentially here, we have enough information that we can substitute in. So this is 0.0025 for AB plus 0.3 for DCE, the mass moments of inertia, plus the mass of AB, which is 1.6 times R G relative to C, 0.0625 in meters, that's squared, times omega 1, which is 5. And this is equal to IAB 0.025 plus 0.3 plus 1.6, the mass of the tube, times Rg relative to C is 0.4375, again in meters, that's squared, multiplied by omega 2. So again, we have a long equation, but we have only one unknown. And hence we can find the unknown which we require, which is omega 2, the angular speed or the rotation when the tube strikes end B of the rod, and it's 2.5359 radians per second. So the angular velocity after the plastic impact of the tube against the end B is equal to 2.54 radians per second, and we've chosen the direction anti-clockwise. So now we need to turn to the kinetic energies, and this will be this is part A. Our answer for part A is the angular velocities. For part B, we wish to calculate the amount of energy that's lost between position A and position 1 and position 2. So we'll look at the kinetic energies of each position. So the kinetic energy T is equal to a half I AB omega squared, where omega could be omega 1 or omega 2, plus the kinetic energy. That's due to the tube. The second kinetic energy is due to the rod, I dCe, times omega squared, where again omega could be 1 or 2 depending on the position, plus the kinetic energy due to the mass center of the tube, a half MAB V bar squared. Again, could be V bar 1 or 2. So that's a general equation for the kinetic energy. So applying it for position 1, the kinetic energy is a half times 0.0025 for IAB times omega 1 squared, which is 5 squared, plus a half into 0.3 for IDCE. Again, omega 1 is 5, and that's squared, plus a half into the mass of the tube, which is 1.6 kgs, times its linear velocity squared, which is the radius 0.0625 squared times omega squared, which is again 5 squared. And solving for this kinetic energy, we get 3.859375. So we're just keeping as many decimal points as possible, and that's joules. If we do this, a similar calculation for the kinetic energy at the second position, we get a half into 0.0025 times omega 2 squared, which is 2. We calculated omega 2 above in part A. So this is 2.5359 squared plus a half into IDCE, which is 0.3 multiplied by 2.5359 squared plus a half into 1.6 times 0.4375 squared times omega 2, which is 2.5359 squared. So we just replace the linear velocity with r times omega. And if we solve for the kinetic energy in the second position, we get 1.9573 joules. So the energy lost in this plastic impact is simply the difference in the two energies. So the energy loss is equal to the kinetic energy in position 2 minus the kinetic energy in position 1. And if we take our two values for T2 and T1 from above, we get that T2 minus T1, as we can see, T1 minus T2 in this case, since T1 is higher, the initial energy minus the final energy. So the energy lost is 1.902 joules.